Welcome everyone. So in this video we are going to solve another set of questions from the so-called worksheet 2. Forget worksheet 2, it's about the questions which matter. I'm going to have every question displayed to you before I discuss or solve them. Now the first two questions I have solved here. The first one first. This is an MCQ, so I've written the question on the board. The weight of a body of mass 0.5 kg on Earth will be. So how do we go about solving this? The weight of a body. So mass is 0.5. We know that W is equal to M into G. So in this case 0.5 is the mass and G, well, you can pick 9.8 or 10. In this case, go by the answer choices. As I have stated in earlier videos, that whenever we are free to choose the value of G, pick the value of G which helps us, which makes things convenient for us. Doesn't mean you can pick any value of G. I'm talking about the choices 9.8 or 10. Sometimes it makes more sense. It makes things easier for us if we pick G is equal to 9.8, because given other data in the question, it gels, I would say, with the other values. In this case, it's 4.9 and things like that. So if I multiply this by 9.8, it comes to 4.9, and that makes the answer choice B correct. That's the first one. Now the second question, the question is here for you to see. The weight of a person is about 1 by 6 times that on Earth. Well, this is known, no big deal. We know that a person or any object weighs 1 by 6th on Moon as compared to his weight on Earth. Now the question is, if he can lift a mass of 15 kg on Earth by applying a certain force. By applying a certain force, he can lift a mass of 15 kg on Earth. So by applying the same force on Moon, what mass will he be able to lift? So long story short, he applies a certain force on an object of mass 15 kg and he is able to lift it. Or he applies 15 kg, he applies a certain force, and by applying that force he picks 15 kg of a mass on Earth. Now the question is, if he applies the same force, how much mass will he be able to pick or lift on Moon? So in this case, let us go by what all we have. It's given that weight on Moon by weight on Earth is 1/6. Weight we know is mass times acceleration. Mass of a body will remain the same. The mass of any body will remain the same. This is not going by the data of this question, folks. This is just a generic equation. Mass times acceleration is weight. So when the ratio of the weight of an object is 1 by 6, we can actually derive the value of the acceleration of the ratio rather of the acceleration due to gravity on these two places. So the acceleration due to gravity on Moon, the ratio of the acceleration due to gravity on Moon to that on Earth is 1 by 6. This is what we have. So from this you see that the acceleration due to gravity on Earth is 6 times that on Moon. So the acceleration due to gravity on Earth is 6 times the acceleration due to gravity on Moon. This is something that we have derived. This is generic derivation which we are going to make use of in solving this numerical. Now on Earth, the force applied, now we are lifting it up. So the force applied is mass times acceleration, and the acceleration is the acceleration due to gravity on Earth, because this is the force applied on Earth. Now it's given that on Moon the person applies the same force. The person applies the same force on Moon, and that's the reason why F is the same as the equation 1 that we saw here, So here again it is mass times acceleration. Here the mass that we are talking about is the mass that we are going to now find out, the mass that we are going to calculate. By applying that force, he could pick 15 kg on Earth, or he could lift 15 kg on Earth. By applying this force, how much will he be able to lift on Moon is what we have this mass for, M. gm, mass times acceleration. This acceleration due to gravity is the acceleration due to gravity on moon, because obviously this time the acceleration due to gravity on moon is what is going to apply. Now from 1 and 2, we know that 1 and 2 are the same. That's because the left hand side is the same force. So if you solve this out, you get this equation, and from what we got earlier, the acceleration due to gravity on Earth is 6 times that on moon. We substitute GE is equal to 6 GM, and eventually you get M is equal to 90 kgs. Intuitively, you would have guessed the answer even earlier, that the acceleration due to gravity on Earth is 6 times that on moon. So something is being attracted more fiercely, I would say, on Earth. So obviously the effort involved in lifting something which will be much more on Earth. So if we are able to pick or lift only 15 kgs on Earth, we will be able to lift 15 into 6, that is 90 kgs on moon by applying the same force. Now in this question, question number 16, as you can read the question, the figure given below shows the same block of wood floating in 3 different liquids. Now you can see from the picture that the block of wood is floating in all 3 cases, but here there is a significant portion of the block which is outside the water. Now again, in all 3 cases, the piece is floating on water or floating in the liquid, not water. Let us not say water because there are 3 different liquids. They're all floating, but the portion of the object is immersed differently. There is some portion which is immersed over here. There is a lesser portion, there's a smaller portion which is immersed. In this case, there's very little of this wood that is immersed. Now, there are some things that we must know before we can really make out which liquid has the highest density. That's the question. Which one as to A, B or C has the highest density of the liquid is what we are talking about. So in this case, how it goes is, whenever, this is generic, if the density of the object is greater than the density of the liquid or the fluid, let me put it this way, density of the fluid, that's a generic statement. So if the density of the object is greater than the density of the fluid, the object will sink all the way to the bottom. None of these is a case of this. So we are talking about a different case. This is just a generic statement for understanding. If this had a greater density than the density of the liquid or the fluid, it would have sunk. But because it has not sunk, it only means that this case is not applying in any of the 3 cases. Now let's come to the third one. If the density of the object is less than the density of the fluid, the object will float. So in all 3 cases, this condition is working, which means the density of this object is less than the density of the fluid. Now you can see that this is applying the maximum force upwards. The buoyant force is the maximum over here. No wonder the same block of wood in all 3 cases we have, but in this case there is only a small portion which is able to get in. Look at it this way. Don't think about Archimedes principle for a moment. Now just see that in this case the block has managed to submerge only very little. There is only a very little portion of the block that has got immersed, which means that the upthrust or the buoyant force is the maximum in this case. The buoyant force is the maximum in this case, and the buoyant force is maximum when the density of the fluid is the maximum. So in this case, C is the answer. Whose density is the maximum? It is C. Now for a detail on the Archimedes principle and how density and the buoyant force are related, you can view my other video. It's a video that I posted in YouTube. You can just search by Archimedes Principle and buoyant force, focus on concepts, and you will get to know the in and out of how this works. Question number 17, a piece of copper of mass. So it's given that the mass of the copper piece is 106 grams and the volume of the water displaced. Look, in this case, the body is dipped in water, and as a result, the water mark changes from 22 ml to 34 ml. Obviously, the volume is 34 minus 22. 12 ml is the volume of the water displaced. So the volume of the water displaced is also the volume of the object or the mass. So the volume of the copper piece, therefore the volume of the copper mass, this is answer to the first part, is equal to 12 ml, or 12 ml is same as 12 cc. So that's the answer to the first question. The second part, density of copper. Now density of copper is equal to mass by volume. You know, mass by volume is density. So in this case, the mass is 106 and the volume we just calculated as 12. So this comes to 8.83 gram per cc. That will be the density of copper. So for question number 18, I have written this question on the board. This is an MCQ. So as you can see, two bodies are stated to have the same mass. Now let's say the masses of these two bodies are m, because they have the same mass. We can call m as their masses. So this is given by volume into density. We know that mass is equal to volume into density. It's a simple question. Well, they can't have the same density. No, they don't have to. Same volume. No, they don't have to. The same ratio of density to volume. No, that's not the correct one either. This is the right answer. It's the same product of density and volume. So if the first one, let's say we are talking about body 1 and body 2. This one has V1 into D1 and this one has V2 into D2, and both are equal to m. Then that implies V1 into D1 is equal to V2 into D2, and that makes this as the right answer choice. That's question number 18 for you. So question number 19, it is a question involving figure. I'm not drawing this, I'm not going deep into this because it's a simple question. It asks about the figure. I will just tell you what the figure says. If there are two figures, and in one a spring balance measures the weight of a body in air, and it shows 30 gf. So in the first case, the weight of the body is 30 gf, and that's measured in air, and W2 of the same body is 28 gf when it is immersed in water. Immersed in water or immersed in some fluid. Yes, in fact, it is water. So we are asked to find out the loss in weight. So it's a no-brainer, I would say. The loss in weight is equal to W1 minus W2, as you can see. So this is 30 minus 28 gf, and this is 2 gf, and I'm sure you know why this body has lost weight. It has lost weight because when it was in water, an upward force called buoyant force is also acting on it, which is opposite to the gravitational force, and that's the reason why the weight of this body becomes 28 GF. Question number 20. So you can read this question. A solid object has a ball weighing 2 kg of density 2000. So there is a ball whose mass is 2 kg. The ball has a mass 2 kg and its density is given 2000. Now the density of water is 1000. This ball is immersed completely. It's given that this ball is immersed completely in water. The density of water being 1000 kg per meter cube, and we have got to find the buoyant force. Now what is buoyant force? Buoyant force is what? Buoyant force is equal to the weight of the liquid displaced. It's equal to the weight of the liquid displaced by the ball. Yes, it is equal to the weight of the liquid displaced by the ball. So in this case, can we calculate the weight of the liquid displaced? So we can calculate the weight of the liquid displaced as mass into G. Mass of the liquid, that is. This is mass of the liquid. Let me write it down this way. This is the mass of liquid into G. Mass of the liquid displaced. Mass times G. M into G is the weight. So mass of the liquid displaced. Now we know that mass of the liquid is equal to volume of the liquid displaced. Volume of the liquid displaced times density, because mass is equal to volume into density. We know this already. So volume of the liquid displaced into density into G. Now how much is the volume of the liquid displaced? We don't know, but we can find out from this given information. Because this ball is completely immersed in the water, the volume of the water displaced is equal to the volume of the ball, is it not? The volume of the liquid displaced is equal to the volume of the ball. So from this information, can we not find the volume of the ball? The volume of ball is equal to mass divided by density. So that gets us 2 divided by 2000. And this, because this is in kg and kg meter cube, volume would come to 2 by 2000, and that comes to 1 by 1000 meter cube. This, folks, is the volume of the ball, which is also equal to the volume of the liquid displaced. Why? Because the ball is completely immersed. So this gets us 1 by 1000 into the density of water is 1000 into G. Let's take this as 10. So 10 Newton is the buoyant force. FB comes to 10 Newton. That's the answer. Question number 20. So you can read this question. A solid object has a ball weighing 2 kg of density 2000. So there is a ball whose mass is 2 kg. The ball has a mass 2 kg and its density is given 2000. Now the density of water is 1000. This ball is immersed completely. It's given that this ball is immersed completely in water. The density of water being 1000 kg per meter cube, and we have got to find the buoyant force. Now what is buoyant force? Buoyant force is what? Buoyant force is equal to the weight of the liquid displaced. It's equal to the weight of the liquid displaced by the ball. Yes, it is equal to the weight of the liquid displaced by the ball. So in this case, can we calculate the weight of the liquid displaced? So we can calculate the weight of the liquid displaced as mass into G. Mass of the liquid, that is. This is mass of the liquid. Let me write it down this way. This is the mass of liquid into G. Mass of the liquid displaced. Mass times G. M into G is the weight. So mass of the liquid displaced. Now we know that mass of the liquid is equal to volume of the liquid displaced. Volume of the liquid displaced times density, because mass is equal to volume into density. We know this already. So volume of the liquid displaced into density into G. Now, how much is the volume of the liquid displaced? We don't know, but we can find out from this given information. Because this ball is completely immersed in the water, the volume of the water displaced is equal to the volume of the ball, is it not? The volume of the liquid displaced is equal to the volume of the ball. So from this information, can we not find the volume of the ball? The volume of ball is equal to mass divided by density. So that gets us 2 divided by 2000. And this, because this is in kg and kg meter cube, volume would come to 2 by 2000, and that comes to 1 by 1000 meter cube. This, folks, is the volume of the ball, which is also equal to the volume of the liquid displaced. Why? Because the ball is completely immersed. So this gets us 1 by 1000 into the density of water is 1000 into G. Let's take this as 10. So 10 Newton is the buoyant force. FB comes to 10 Newton. That's the answer. This is question number 21 for you. A solid object has a weight 3 newtons. When it is immersed fully in water, it weighs 2.5 newtons. So find the density of the object. Well, let us take baby steps in solving this question. Small steps. That's what I mean when I say baby steps. What do we interpret? A solid object has a weight 3 newtons, and when it is immersed, it weighs 2.5 newtons. So you would agree that there is some loss in weight. This loss in weight is because of the buoyant force. So whatever loss in weight this object has experienced is because of the buoyant force. So is it not fair to say that the buoyant force acting on this object is 0.5 Newton? Yes, it's because of the 0.5 Newton equivalent buoyant force that the overall weight of the object has reduced by this much, 0.5 Newton. So in this case, it's given that the density of water is 1000. G is also given as 10 meter per second square, and we know that mass times acceleration is the buoyant force. So let us keep it at this for now. We have established that the buoyant force is 0.5 Newton, that's the loss of weight, and we also know that buoyant force is equal to the weight of the liquid displaced. So if m is the mass of the liquid displaced, where m is the mass of the water in this case, if m is the mass of the water displaced, then you would agree that m times g is the buoyant force. Now let us come to this part of the board. Mass of the water displaced, that's m, let's say. We've already taken this as m. That is equal to v times density. We know that mass is volume times density. So the mass of the water displaced is the volume of the water displaced into the density of water, and the weight of the water displaced is mass times g. So let us first figure out what this will be. In this case, the weight of the water displaced is 0.5 Newton. We know that. This is mass times acceleration. G is given as 10. So from this you can see that the mass of the water displaced comes to 50 grams. 50 grams is the mass of the water displaced. Now if you revisit this equation, 50 gram, that is mass of the water displaced, is volume of water, which is 50 cc, into density of water, which is 1 gram per cc. So from this, the volume of the object is determined. Why? Because this body is completely immersed in water, and if therefore the volume of the water displaced is 50 cc, it would mean that the object has a volume equal to 50 cc. So from here we can join rather all the missing dots, I would say. We can connect all the dots. So volume is given by mass by density. Now in this case, volume we found out to be 50, and mass is given. Mass is not given, but we can find out. The mass of the object is 3 newtons. The object is 3 newtons. So that gets us what? The mass will be 3 by 10 kg, and that is equal to 300 grams. So in this case, 50 is equal to 300 divided by density, and therefore the density will come to 300 by 50 gram per cc, which is 6 gram per cc. That's the density of the object. That's the density of the object. Question number 22, a very interesting question. The volume of a 900 gram of a substance is 1000 centimeter cube. So whenever we have questions like this where some data is given and we can readily infer some, it's a good idea to write the inferred data. What I mean to say is mass is given as 900 gram. I've just converted this to 0.9 kg in case this is required somewhere. It's given that the volume of this object is 1000 centimeter cube. So we can readily determine density, which is given by mass by volume, and it comes to 0.9 gram per cc. Now it's also given that the density of water is 1 gram per cc. Now when, in this case, look, the density of water is greater than the density of the object, in such a case, the object floats. The object floats. The density of the object must be greater than the density of the fluid to sink. In this case, the density of the object is less. The density of water is more, and therefore the object floats. So the first part of the question, the object floats. Will the substance sink or float? The answer is the object floats. Now the second part of the question, what will be the mass of the water displaced by the substance? Now this question is answered in different ways by different people. I think I'll tell you a simple way to remember what really happens. Now we know that the body has not sunk, it is floating. Yes? So when a body is immersed in a liquid or a fluid, there are two forces at play. We know one is the gravitational force, which is the weight of the object, and the other is the buoyant force, the force that is applied bottom up. Weight top down, buoyant force bottom up. Now in this case, if something is to float, we must bear in mind that the object, the weight of the object, would have been balanced by the buoyant force. I repeat, the weight of the object which is acting downwards has to be balanced by the buoyant force acting upward. Only then the body will stop sinking and it will stop somewhere. That's the logic, that underlying logic, I would say, that we have applied in this question. Now the weight of the mass is equal to the buoyant force. The weight of the mass is equal to the buoyant force. That's how the body has stopped going down. It has stopped at one point and it's not sinking any further. Now let us find the weight of the mass. Weight of the mass is easy to find. It is mass of this object times acceleration. We have assumed the acceleration to be 10 meter per second square. So in this case, the buoyant force, which is equal to the weight of the mass, is 0.9 kg multiplied by 10 meter per second square. So 9 Newton we know is the weight of the body, which is also equal to the buoyant force. So we now know the buoyant force, that is 9 Newton. Mass of the water displaced into G is that not the buoyant force? The buoyant force is what? It is equal to the weight of the liquid displaced. So weight is mass times G, and that's equal to 9 Newton. Therefore, the mass of water displaced will come to 9 divided by 10, because G is 10. So it comes to 0.9 kg, which is 900 grams. Interestingly, you will see that the mass of the object, which was 900 grams, is equal to the mass of water displaced, which is 900 grams. This happens when the body floats. Whenever a body floats and does not sink, this is generic, something that you must remember. You'll do good to remember rather. When a body floats, its mass is equal to the mass of the fluid displaced. The mass of the object being immersed is equal to the mass of the liquid that is getting displaced. And that's how the two balance each other. That's the answer for you. Question number 23. Easy question. If the density of aluminium is this much, then what will be this value in CGS system? Now we know that in CGS system, mass is measured in grams and length or distance is measured in centimeters. So all we need to do is to convert these quantities into the units in CGS system. So 1000 kg to grams will be 1000 grams divided by meter cube into centimeter cube. So mind you, it will be meter into meter into meter. So it will be 100 centimeters into 100 centimeters into 100 centimeters, and that will make it centimeter cube. So in this case, as we see, there are 5 zeros here and 6 zeros here. So it will eventually come to 3.7 gram per cc, and that will make it answer choice D as the correct answer. So, and I'll write the answer choices as well. 3700 gram per cc. B is 370 gram per cc. C is 37 gram per cc, and D is 3.7 gram per cc. So I see this as the correct answer choice. All right, so that was question number 23. The density of the iron ball is given. It's 7.8 gram per cc, and the volume is also given, and we are required to find the weight in air. So weight we know is mass times acceleration due to gravity, where m in this case we can find out using the values that we have. So this comes to 350 into 7.8, and this will come in grams. Yes, so this divided by, we can then divide by 1000 to convert this to kg. So let us calculate this. 350 into 7.8. One decimal point. So this comes to 2730 by 1000 kg, which means it is equal to 2.73 kg. That's the mass. Now weight will be, therefore the weight will be mass times density, mass times acceleration due to gravity, and this will be 2.73 into 10. You can assume the value as 10. Assume G is equal to 10 meter per second square, and that makes it 27.3 newtons. So question number 25, we have the density of some substance, turpentine oil, known, which is 840 kg per meter cube. What is its relative density? Well, relative density of a substance is given by the density of substance with respect to the density of water. And in this question, the density of water is also given. So all we need to do is to divide the density of the substance, which is 840, divided by the density of water, which is 1000, and the answer comes to 0.84. Mind you, there will be no unit here because this is relative density. Relative density has no unit. This is 0.84. So this is a case study question. Again, just make sure that the effort or time you spend in reading the case study is optimum. You can actually skim through the questions, a quick glance, to see if you are able to solve these questions even without reading the case study, or maybe by looking at the case study only superficially. Again, this is not a generic rule. Don't take my statement as a final statement which applies in all cases, but this is, I have seen this to be the case many a time. You can probably just go through the case study at a very high level, or maybe go to the question and see if you're able to answer. Like the case study question, in this case, all questions that I see can be answered even without reading the case. So in this case, the first question, what is upthrust? And it's an MCQ. So upthrust is actually equal to the weight of the liquid displaced by the body. This is also called buoyant force, mind you. The buoyant force is what? It's equal to the weight of the liquid which is displaced by the body. In general, this is fluid. Now, what is that upward force called? It's buoyant force. We all know that. What is the principle of flotation? It states that when the body being immersed in the fluid has a density which is less than the density of the fluid. I repeat, when the body being immersed has a density less than the density of the fluid, then the body will float and will not sink. This is the law of principle of flotation. Now, in the last question, which is the fourth bit, we have why is it that when a plastic piece is immersed in water, it is thrown up, rather it just comes to the top. It's because the density of the liquid, in this case water, being greater than the density of the object being immersed, the buoyant force wins. Mind you, the buoyant force is much more than the weight. The buoyant force is greater. It wins, it prevails over that body, and therefore the body is thrown up. If you apply some force and try to push it down, the moment you remove that force or remove your hand, you will see that the body comes back to the top because the buoyant force wins. That explains the case study. So with this, we have answered all the questions in this particular set. You can, as I stated earlier, you can go through my video that's on YouTube titled Archimedes Principle and buoyant force, which details the in and out of this process. So most of the questions that we have tried solving in this set will become easier, I'm sure, if you have really spent some time going through that video. Thanks all for watching.